Okay, now we're going to begin with the actual physics part of the course, and we're going to begin with this topic of mechanics, which I spoke about in the introduction. And more specifically, we're going to start this second chapter, deals with Newton's first law of inertia. Now, this all starts with Galileo, who had a very famous thought experiment concerning motion. Previous to this, Aristotle thought that the natural state of an object was to come to rest. And this is understandable because he observed that balls or rocks or whatever that moved along the ground did eventually come to rest. Galileo, however, noticed that if he took a ball and he rolled it down a hill, it picked up speed. And if it went up a hill, it slowed down. So he concluded that if a ball was moving horizontally, shouldn't it move with constant speed, indefinitely really, if friction was not present? Well, Newton expanded on this concept, as we'll see in the next slide. Newton's law of inertia states that an object continues to move with uniform motion unless acted upon by a non-zero net force. All right, so there's a couple of words here that are very important. First of all, the word continues. So in other words, the object is going to change, it's going to resist changes in its motion unless acted upon by a non-zero net force. Uniform motion, well, what does that mean? Well, it means that the object is either going to be at rest or it's going to be moving at constant speed. So since it's going to resist changes in its motion, this property of matter that's responsible for this resistance is called inertia. Now, the other thing that's very important about that law in the previous slide is this notion of the sum of the net forces is zero. Well, first of all, a little vocabulary. When the sum of the net forces on an object is zero, we call that equilibrium. We say that the object is in equilibrium. Okay, well, what does this mean when the net forces are zero? Well, first of all, forces are vector quantities, and vector quantities always have direction, and you have to take into an account their direction when you combine vectors. So, here's a couple of examples. If you've got a force of 10 newtons east and 10 newtons west, and you're adding them together, the sum of those two is actually zero because they're acting in the opposite directions. On the other hand, if you've got 10 newtons east and 10 newtons east, well, that adds up to the sum of those is 20 newtons east. So Newton's law of inertia states that if the net forces on an object are zero, then we know that the object is going to resist changes in its motion. It's either going to be, if it's at rest, it's going to stay at rest, and if it's moving at constant speed, it's going to stay at constant speed. So another way to look at this is if an object is moving at constant speed, therefore it must be in equilibrium, or the net forces, the sum of the forces on it must be zero. If an object is at rest, it also must be in equilibrium. The law of inertia applies. The sum of the forces on the object must be zero. So here are some examples. A book is resting on a table. Is it in equilibrium? Yes, it is. And the reason is because it's at rest. If it's at rest, Newton's law of inertia says that the sum of the forces on it must be zero. Car is traveling down the road at constant 60 miles per hour, assuming it's in a straight line. Is it in equilibrium? Again, the answer is yes. You might ask, well, we know that there must be a force on the tires due to the transmission and so on. The car is using gas. But on the other hand, friction is a force, and so is air resistance, and so it must be that forces due to friction and the forces being applied to the tires are exactly canceling each other out so that the net force on it is zero. How about an elevator moving upward at constant speed? Again, yes. If it's moving at constant speed, doesn't matter whether it's upward, downward, sideways, whatever, the elevator must be in equilibrium. Holding your book over your head without moving, is it in equilibrium? Again, the answer is yes. You might feel the weight of the book on your hands, but you are applying an upward force and supporting it, and so therefore, again, the object is in equilibrium.